This is the first ever atomic bomb, less than half a millisecond after detonation. A fireball 60 meters across, hotter than the sun's surface. Science, however, has come a long way since this. But just how far exactly? And how did we get there? It is quite possible that the development of nuclear weapons was the consequence of a single letter signed by Einstein. It was written by a man named Szilárd Leo. Born in Hungary and having been refused entry to the Budapest University of Technology for being Jewish, Szilárd moved to Berlin, where he had worked on a number of inventions, one of them in collaboration with Einstein. In 1933, Rutherford, who was a pioneering researcher in nuclear physics, had given a speech in which he dismissed the idea that the transformation of atoms could be practically harvested for energy. Szilárd was so upset by the dismissal that the same day he devised the idea of nuclear chain reactions, despite the not yet discovered mechanism of nuclear fission. Having received news that scientists in Berlin had achieved nuclear fission by bombarding uranium with neutrons, Szilárd had immediately set out to acquire uranium oxide and had conducted a simple experiment to shoot neutrons at uranium with a physicist named Walter Zinn. They turned on the machine and nothing happened. That is until Zinn realized it was not plugged in. After plugging it in, the machine worked.
We turned the switch and slowed the flashes. We watched them for a little while and then we switched everything off and went home.
This was still not a chain reaction, but the implications were massive.
That night, there was very little doubt in my mind that the world was headed for grief.
It was after this that Szilárd decided to write a confidential letter to President Roosevelt. He wrote about the possibility of nuclear weapons and the fear that Germans could be developing them. Thus, he encouraged the US to begin development themselves. He visited Einstein at his summer resort and explained his findings as well as the theory behind such a weapon to him. Einstein listened to his explanation in silence and at the end of it responded,
I haven't thought of that at all.
Einstein would then make what years later he would consider his biggest mistake in life. He signed the letter. Roosevelt, unable to turn a blind eye to the letter, called for action, and while the initial focus was not the development of a weapon, it was the first step into government-backed research into nuclear fission, and it would eventually lead to the creation of the Manhattan Project. With the Japanese attack on Pearl Harbor in December of 1941, the US had no choice but to enter the war, and thus a greater urgency was felt to develop weapons capable of mass destruction. But the right people were needed for the job to make sure it wasn't a waste of time. Robert Oppenheimer invited a large number of physicists to meet in July of 1942, and collectively they came to the conclusion that a fission bomb was theoretically possible. The problem was resources. Uranium was essential for the project and it was difficult to come by. The Belgian Congo, being in Allied hands, ended up providing most of the uranium ore. This ore, however, consisted mainly of the 238 isotope, which isn't fissile, meaning it cannot experience a chain reaction when hit by low-energy neutrons. The other small percentage is the 235 isotope, which is very much fissile. In a process called uranium enrichment, the percentage of the fissile isotope can be increased. The earliest attempts at this used centrifuges, which while possible on a small scale, proved much too expensive and difficult to maintain industrially, as tens of thousands of centrifuges would have been needed. In the end, 3 other technologies were used in line, where the first stage was thermal diffusion, which enriched the uranium from the 0.78% to 0.89. The second stage was gaseous diffusion, which brought the percentage up to about 23%. Finally, electromagnetic separation boosted it to 89%. 50 kilos of this enriched uranium were produced by the end of July 1945 and would be used in the Little Boy bomb along with some 50% enriched uranium. The other fissile material produced by the Manhattan Project was the isotope 239 of plutonium. To do so, natural uranium was bombarded with neutrons, turning it into uranium-239. This isotope only had a half-life of 23 minutes, after which it decayed into neptunium-239 and plutonium-239. The plutonium created through this process would be assembled into the first ever nuclear weapon, the design of which was still up to debate. A number of ideas were proposed, initially leaning towards a gun-type weapon where two subcritical masses would be assembled into one to create a chain reaction. This would happen due to the fact that with a larger mass, naturally emitted neutrons would have a lesser chance of escaping without being absorbed. As it turned out, however, the plutonium had a high concentration of the 240 isotopes, which made spontaneous fission more likely. And so in a case of a gun-type weapon, it would react too quickly, leaving most of the plutonium out of the chain reaction in what's known as a fizzle. For this reason, the scientists moved toward an implosion design. This was a lot more complex since it required the manufacturing of explosive lances and the very accurately timed detonation of high explosives. The force of the explosion would compress the plutonium into a smaller area, once again making the escape of naturally emitted neutrons less likely. With that all said, the bomb was designed and completed by summer of '45, and now it was time to find the right place to blow it up. A remote area in the middle of New Mexico was chosen for the test, where a 30-meter tower was constructed. The device would be detonated at the top to better understand the effects of a bomb that would be dropped from a plane and detonated in the air. The detonation was scheduled for the early morning of July 16th. A storm had postponed the countdown, but thankfully it passed without causing any issues. And at around 5:29 in the morning, the countdown had reached the final 10 seconds. Needless to say, the test was successful. With an estimated yield of 25 kilotons of TNT, the fireball reached 210 meters in diameter at its peak. With two more bombs close to completion, the big question arose: should they be used in combat? For those working at Los Alamos, there was not much say in the matter. Szilard did, however, start a petition that was signed by 70 scientists. The Manhattan Project's original goal was to defend from a possible German nuclear attack, but since Germany had been defeated back in May, Szilard advised against the usage of the bombs to settle matters with Japan diplomatically. He also called for nuclear power to be put under international control to avoid an arms race. The petition never made it to President Truman, and the two bombs would eventually detonate over two Japanese cities, resulting in the deaths of over 100,000 people. Scientists have now harnessed the power of the universe's building blocks, but they weren't done. In stark contrast to the splitting apart of atoms, namely fission, some scientists were greatly intrigued by fusion. Specifically, Telerede, another Hungarian emigree, was already working on such a concept even before the Trinity test. His idea was the usage of a fission/atomic bomb to implode fusion fuel, to make the escape of neutrons even more difficult. After the end of World War II, he collaborated with Polish mathematician Stanislaw Ulam to design the Super. Encased in a material that will reflect radiation, plus a lead liner to have direct X-rays, the weapon consisted of two stages. The primary was a fission bomb, essentially no different to the one used at Trinity or the Fat Man dropped on Nagasaki. The second stage consisted of fusion fuel, in this case liquid deuterium mixed with tritium cooled to near absolute zero with liquid nitrogen. A spark plug of plutonium is included in the middle of the stage, the whole of which is then covered by uranium as a temper. The remaining space is filled with polystyrene foam, and a battery is included for the initial charge. The detonation of such a weapon starts with the explosion of the fission stage. The X-rays emitted are reflected around in the foam, heating it into plasma, which then compresses the second stage. The compression causes the spark plug to fission. The deuterium-tritium mixture, compressed and heated from all directions, undergo fusion, releasing high-energy neutrons which cause the uranium temper to fission. This fission is where the majority of the weapon's yield comes from. The first such weapon constructed was on Enewetak Atoll, although it resembled more of a factory. Nicknamed Mike, the detonation took place on the 1st of November 1952. A fireball over 5 km wide had swallowed the island whole, and a white mushroom cloud rose above the clouds, but there was no time to be mesmerized. An hour after detonation, F-84 Thunderjets were sent into the mushroom cloud to collect samples. First, pilot Virgil K. Mironi entered the cloud and after 5 minutes successfully collected the necessary samples and exited the dangerous area. Next up was Jimmy Priestley Robinson and Captain Bob Hagen. While Moroni completed his task without any complications, these two were about to have a very different experience. While inside, Robinson had encountered extreme turbulence, knocking him unconscious. He managed to regain control of his aircraft shortly after. However, both him and Hagen had their instruments disrupted by the electromagnetic storm. Unable to locate the refueling aircraft, both were forced to attempt an emergency landing. And while Hagen managed to glide to an airfield, Robinson wasn't so lucky. His heavy jacket, designed to protect him from radiation of the cloud, had most likely restricted him from making it to the surface, and thus, his body was never found. Robinson was among the first accidental casualties of nuclear weapons, but he sure wasn't the last. In search of more practical thermonuclear weapons, the US began experimenting with lithium deuteride, which is solid at room temperature as opposed to the liquid form. With no need for a cooling apparatus, the bomb was reduced to under 11 tons, which meant that it could be delivered by bombers. The device, nicknamed Shrimp, was detonated in the test called Castle Bravo on the 1st of March 1954. The expected yield was 5 megatons. The scientists, however, made a grave mistake. The bomb had an actual yield of 15 megatons. This would lead to the worst radiological disaster in the history of the United States. This was due to an element called lithium-7, which made up a good percentage of the fusion fuel. Scientists had incorrectly assumed the lithium-7 to be inert, while in reality it underwent fission, creating more tritium to aid the fusion and also releasing another neutron. The bomb was also detonated regardless of the borderline unacceptable wind conditions. The resulting fallout spread across hundreds of kilometers of ocean, including inhabited islands, which had to be evacuated, though this only happened 48 hours after the explosion. Some years later, they would be allowed back, but anyone who went back were greeted by the sight of their staple foods such as all fish gone. A Japanese fishing boat had been directly hit by the fallout. One aboard died 6 months later from the radiation exposure, and another had a baby who was stillborn and deformed. In fact, it was later discovered that much of the fish caught in the Pacific Ocean had been contaminated with an unhealthy amount of radioactive material. A mission that was meant to be kept secret became an international incident. The outcry in Japan had become so loud that a political agreement was reached for the US to aid the country with $15.3 million as compensation for those affected. Meanwhile, the Soviet Union was working on something even bigger, a theoretical 100 megaton bomb codenamed Ivan. It was most likely a 3-stage device, although the exact configuration is debated to this very day. It was made clear by Yuri Trutnev, who worked in the Soviet nuclear program, that two 2-stage thermonuclear modules were placed on either end of the bomb, in what is known as a bifilar design. These two compressed the much larger thermonuclear module in the middle. Due to the fear of fallout, the uranium temper was switched to lead, halving the bomb's yield. It was carried to its test location via a modified Tupolev Tu-95 and escorted by a Tu-16 with science gear. The planes were coated with reflective paint. Despite this, the crew of the bomber was only given a 50% chance of surviving the mission. On the 30th of October, 1961, humanity would detonate the largest bomb in history, and decades later it would go by the name Tsar Bomba. The explosion was so massive that its own shockwave deflecting off the ground stopped the fireball from touching down. The same shockwave circulated the Earth 3 times in both the atmosphere and the crust. The bomber crew were not informed of their survival chance, but they completed the mission unharmed, and since the radioactive fallout was minimal, scientists were able to conduct tests at the site just 2 hours later. The Soviets were hoping to showcase their limitless nuclear yield to other nations, and with the shockwave detected all around the world, they definitely made a statement. But combined with the Castle Bravo catastrophe, this only added to the uneasiness of the public, and thus, 2 years later, the Partial Nuclear Test Ban Treaty was signed, putting an end to detonations in the atmosphere. This of course didn't stop the advancement of such weapons. Instead, we enter the era of underground testing. These tests were rampant. To date, 815 separate detonations were conducted by the US, mainly on the Nevada test site. During the explosion of such a test, the rock close to the device vaporizes. The plasma created cools and flows to the bottom of the cavity. After some time, the material becomes unable to hold itself and collapses in, forming a crater on the surface. As such, the Nevada test site transformed into a very different landscape. To carry out so many of these tests, uranium was highly sought after. The government was willing to pay great prices for it in the 50s. With a bit of an exaggeration, a craze had formed around uranium mining, prompting the creation of songs such as Uranium Fever and Uranium Rock. However, most people looking for the radioactive gold were unsuccessful to say the least. Despite this, in the 70s, the US saw a few threats from private citizens supposedly possessing nuclear bombs. But hold on, aren't nuclear bombs supposed to be multi-ton contraptions? Well, after the war, Teller insisted on opening a second lab alongside Los Alamos in Livermore. A toxic relationship had built up between the two labs. After failed tests by Livermore, Los Alamos poked at their misery by distributing images of what they sarcastically called reusable test towers. This didn't demotivate Livermore one bit, however, And the technical lead of the new lab was given to three brilliant physicists whose approach to innovation was simulation-based, in contrast to Los Alamos' experiment-based. Foster's greatest innovation was the suitcase bomb. He managed to reduce the size and weight of a nuke to the point that it could be carried in suitcases. And I suppose you could have launched on top of it too if you'd like. The lab was previously reliant on the crane used by Los Alamos, which would have greatly set them back in their schedule, but Foster had no need for it since the suitcases could be just carried to the top by hand. The tests were successful, and while these bombs weren't destructive on the same scale as the larger ones, they could still level an entire city, and they brought about the fear that one could be easily moved to virtually any location unnoticed. Most of the threats turned out to be unserious, but the need to be able to deal with them still felt important to the FBI, and so NEST was formed, a team specifically designed to search for nuclear threats without alerting the public. On a smaller scale, suitcases with detection hardware would be used, while larger areas could be monitored with helicopters. The US was hit with 18 cases between 1975 and 1989, but thankfully none of them ever led to disaster. Interestingly, the threat of nuclear terrorism never quite made it mainstream. The idea was of course less conceivable than that of the government using the weapons. I mean, is there even such a thing as nuclear weapons being in good hands? Declassified US papers show that they have had over 1,000 oopsies with the nuclear arsenal, some more serious than others. It is nothing short of a miracle that none of them had catastrophic consequences, but it is only a matter of time until one does. Following World War II, the US and USSR funneled a large portion of their resources into manufacturing more nuclear bombs, while making them lighter and more powerful. After the successful detonation of hydrogen bombs, the focus shifted to turning those into deliverable bombs. When rockets began development, it was a no-brainer to combine the two. Of course, rocket development is a feat in and of itself. The trial and error eventually got there, and the first successful test of a rocket was the Russian R-7 on the 21st of August 1957, marking the start of the space race and the age of intercontinental ballistic missiles. These rockets, used for the purpose of carrying bombs, were really no different than rockets used for space travel. Only minor modifications were made to the R-7, which then carried the first man-made satellite to orbit. The Americans' version was the Atlas rocket, which saw its first successful launch just a year later. The focus of both countries shifted to widening their ICBM arsenal, while plane-delivered bombs became fewer. Thanks to Foster and Livermore's innovations, warheads became smaller than humans, which allowed for the first nuclear submarines to be put in service using the compact Polaris missile. The number of warheads began to grow rapidly into the thousands for both supernations the following decade. Feeling the need to protect against ICBM attacks, anti-ballistic missile systems were tested by both sides during the 90s. It composed of rockets which would intercept incoming warheads. These efforts would prove to be wasted, however, when multiple independently targetable re-entry vehicles entered the scene. This system allowed for multiple of the now tiny warheads to fit inside one rocket, up to as many as 16 of them. Each of these would have to be targeted by defense systems, making it economically unviable. With each warhead using less resources, the growth of their count picked up, and the US peaked at over 31,000, while the Soviet arsenal reached just over 40,000 a couple decades later. But thankfully, the following year saw multiple disarmament treaties, and thus a decline in the number of weapons. The warheads in an MIRV were limited too, and by 2017 the US had completely phased out the system. With the Comprehensive Nuclear Test Ban Treaty signed by 187 parties, it was expected that nuclear development would stagnate and the number of warheads would decrease. Except, non-nuclear experimentation is still possible, along with computer simulations. The current stockpile could also be modernized with new manufacturing techniques, and so, the threat of nuclear annihilation is as prevalent as ever. It will just arrive in a warhead with a different name. Today, 6 countries are believed to be in possession of ICBMs, and since modern ones take a mere 30 minutes to reach their targets, we are, in a way, never more than half an hour away from self-extinction.